Okay, good morning, everybody. I've graded your quizzes, and so please pick yours out of the stack and pass it along. Let's take a look at a couple of announcements here. Oh, April 19th, that doesn't make any sense, right? Hold on a second. I think I need to... all right, so that makes more sense. Okay, homework 15 is due on Thursday, November 29th, and cost estimation is what we started in class on Tuesday, and we're going to continue with today. So that'll give you something to do during Thanksgiving besides just eating a lot and going shopping. So are there any questions about what we covered last time or about the announcements before we get into the new material? Okay, we're going to continue in Chapter 15 talking about a cost index method of preparing cost estimates, and then other factors, other methods of calculating cost estimates like cost capacity equations and the factor method. So a cost index is something that you actually may already be familiar with, and sometimes you hear these sorts of things referred to in the news, and let me give you a look at some of the commonly used cost indices. Okay, so here's one that's provided by the U.S. government, and you can see here the website is census.gov. What it is saying is the cost of new family home construction for every year since 1964. And so what they've done here on the index, that's a relative idea of how expensive housing was in that year, and it's a linear scale, so that in every year since then, you can look and see, relatively speaking, how much did housing cost. And so just to tell you like what it would mean, if a house cost $12,000 back in 1964, and that's maybe a pretty average price for a house in 1964, then you can see that the price is increasing over time due to inflation. And what they've done is they've set the baseline to be 2005. That's what it says here at the top, that 2005 they're setting it at 100%. And so that means back in 2005 is their baseline year. They wanted the prices there to be represented every other year to be representative in terms of the prices at 2005. So the house that cost $12,000 in 1964 would cost in 2005 would cost $100,000. And you can get a sense since 2005 how housing prices across the country have increased. So you can see now the index in 2017 was 125.9. And so if you wanted to understand just the price of housing over time, you could use this index. And last time in class I mentioned that sometimes people make the mistake of applying the overall economy's average inflation rate to specific goods that may vary more or less than the overall economy's rate of inflation. Some things are getting cheaper over time. Most things are getting more expensive, but that rate of cost appreciation varies from field to field. And so we can get an index to tell us specifically for the thing that we're interested in how much have prices changed. And this is just an example of an index for housing. Let's take a look at another one. Okay. The CPI is the Consumer Price Index, and this is one that the government puts together to try and describe the expenses that the average consumer faces in their life. And so it looks at, across the country, how do people spend their money, and it looks at the change of prices, and it weights it according to what percentage of the average budget gets spent in that category. So look, for example, they're saying that the expenditure category of food represents 13.2% of the overall weighted basket of costs. And so what they mean by that is they expect that the average American is spending 13% of their money on food. And specifically, they've broken it down even further than that. They have it food at home, and then if we scroll down a little bit, we can find, it's a lot of detail here, food away from home. And so they've broken each of those into even further, like a third order category. So they know how much money people usually spend on cereals and bakery products, less than 1%. Meat, 1.6% of the average American's budget is spent on meat, poultry, fish, and eggs. And so anything that you could think of is in this list of expenditures. They know how much people usually spend on tires. So the average American spends 0.22% of their annual budget on tires, and so on. And so having this idea of what are the weights then allows them to track the prices of each of these different things. And there are government workers whose job it is to go into businesses and check the price of different goods. So there may be someone whose job it is to go into grocery stores in North Dakota and find out how much does wine cost, how much does whiskey cost, how much is beer, ale, and malted beverages. And so they can not only find out how much individual categories are shifting, but they also are able to describe it on a regional basis. And so, prices may vary a lot more in a place like New York City than they do here in West Virginia. And so this is showing for all goods averaged together the consumer price index. And so the one I showed you before was specifically for housing. This is an overall average based on the things that people are buying. And if we look, what is the 100% index year? It looks like in this case the index was set to 100% at, let's see, they've got it month by month. So in between 1983 and 1984 is when they were using as the baseline. And then nowadays we're at 245% of the costs that things were back in 1983-84. So this is kind of an interesting table that tells you how much costs are going up, and there are a lot of things that are tied to this. For example, people who are receiving Social Security or other pensions, their pensions will go up each year to account for this inflation effect. And how much the pension needs to go up is largely dictated by this consumer price index. And so it's a really important figure. And if we're using this type of information for generating cost estimates, there are a lot of sources that are specific to engineering projects. You can get the cost of construction materials. You can get the cost of labor. And so here are just some sources that are mentioned in the book where if you want to get different types of cost data, the different sources that are available that you could use to make a really accurate and detailed cost estimate, and not only detailed, but also projecting it into the future by looking at how much those costs changed in the past. Now this is how that type of data is used. So you need to find out the index in a year where something was known, that's I sub naught, and the cost of what something was in the year that it was known. And you can predict a future cost or a cost in a different year by using the ratio of the index. And so what that means, for example, is if you knew that people were spending $100 per month on groceries back in 1982 when the index was 100, then you could expect that that same $100 per month on groceries would actually require, that same amount of groceries would actually require $245 nowadays. And so that's an illustration of how this ratio is used. Is you find the index value from the year of interest, that's I sub t, and you multiply it by the cost in the year where you knew the cost and the index value at that time. So just to get a feel for how this type of information is used, let's use it to estimate the cost of building a repair garage. And what we have to begin is some data from 2004. A similar garage was constructed in 2004, and we know the cost of construction back then. And so we're going to try and project what will be the construction cost in 2008. What would be the cost in 2008 if we know that these certain categories apply, that 30% of the costs are going to be due to labor, 20% due to materials, 50% due to equipment. Now, this is similar to that percent weighting table that I showed you from the Consumer Price Index. And so what you need to do is you need to find out what's the weighted index in 2004. So rather than just averaging a simple average, a simple average would be add these three numbers together and divide by 3. That's not actually the way that we want to do it. What we want to do is we want to find out the index as a percent of the total cost. And so that weighted average means that you'd multiply 0.3 times the index in 2004 for labor and so on, so that you, in Part A, calculate the weighted index for 2004, and then in Part B, you do the same thing for the weighted index in 2008. And so I'm just going to pause the recording here, give you some time to work, and see if you can figure out what would be the cost of constructing this garage in 2008 based on, we know in 2004 it was $650,000. All right, so let me show you the solution. As I was walking around, I think everybody's definitely on the right track. The 2004 index is 149. The 2008 index is 178.5. And so then if we want to know what the expected cost in 2008 would have been, then it's going to be $778,691. And then if we have from the table the percentage of how much is being spent in each category, then that means the labor would be $233,000, material $155,000, and so on. So this cost index approach is one of the accepted methods that's used for cost estimation. And what it can do is that it can account for not only inflation, so that's the change in prices over time, but it also will help you to account for variations in price by region. And so you could get cost data like this that's specific to Alaska. And remember how we were talking about it wouldn't be wise to project what cost information you might have for constructing a building in California to that of constructing a building in Alaska? Well, you could make that comparison if you had cost-specific data in California and that for Alaska, and then you constructed a ratio similar to this. So you might know, for instance, that steel costs 30% more in Alaska than it does in California. But then maybe labor is less expensive in Alaska compared to the building that you had constructed in California. And so you can account for changes in prices by region, changes in prices by time, and so it's a really important approach. Any questions about this part 1 of the in-class exercise? All right. Here's an aerial photo of a wastewater treatment plant. And maybe you've seen things similar to this as you've been flying across the country. If you look down, most cities will have a wastewater treatment plant that looks a lot like this. What we're looking at here is an aeration basin where they're adding a lot of air so that microbacteria can break down pollutants in wastewater, and then these are clarifiers where sludge settles to the bottom, and so they can purify the water before they dump it into the river. This is a lot smaller, and sometimes there are cost differences that are related to economies of scale. And so we've already just talked about how cost index data can be used to account for the change in prices over time, and also the change in prices from place to place. But you can also take an approach that allows you to correct for differences in size. So the people who built this wastewater treatment plant maybe had a better price on pumps than the people who built this one. You know, maybe since they were buying so many pumps, they got a bulk discount. So there are some things where the pricing becomes more favorable the more that you buy or the bigger the item is. But there are some things actually where the pricing becomes less favorable as you build a larger and larger system. So a cost capacity equation will allow you to estimate the cost effects of size variation. And the way it works is that you find the cost of some item at a certain capacity, and that's what we're going to assign the variable Q1. And it could be related to the square footage of a certain thing. It could be related to the weight. It could be related to whatever parameter you use to describe the size or the amount of something that's going to be purchased. And then you also are trying to, with this equation, predict what's the likely cost of some item at a different amount, so at a different capacity. So in the case of this wastewater treatment plant, maybe what we want to do is estimate the cost of aeration basins. And so you can see this wastewater treatment plant has a really small aeration basin, whereas this bigger plant has many times more. And so if we wanted to find out that cost, then there's a correlating exponent that we have to look up from a table, or it may be given in the data, that tells you whether prices are linear with respect to size, or if there's an economy of scale. So if x is less than 1, what that means is that there's a cost advantage on a per unit basis for larger sizes. And so that means the more you buy, the less it's costing per unit if x is less than 1. There are some things, though, where there's a diseconomy of scale, which means the bigger you make it, the more expensive it becomes. And so let's look at a table that kind of illustrates some of that data. On this table that's in your book, table 15.6, it's talking about, for wastewater treatment, different correlating exponents, and you can see some of them are less than 1, meaning that there's an economy of scale, and some of them are greater than 1, meaning it's a diseconomy of scale. So some of the things that are less than 1, for instance, one that's quite a bit less than 1, this chlorine plant. And so that's the type of equipment that's generating chlorine, so it can be used for disinfecting water. The bigger you make that chlorine plant, the correlating exponent is less than 1, means that it's still going to cost more for a bigger item, but the rate of cost increase slows. Whereas some things, like sludge drying beds, have a correlating exponent of greater than 1. So what that means is that if you built a sludge drying bed that's 100 square feet, it would cost, let's say, $100. But if you wanted to build one that's 200 square feet, then it's not just going to be double the price. It's going to be more than double the price to make it double the size. And so that's what this correlating exponent means, is that if you increase the amount that's being purchased, do you get a discount per item? Is it roughly the same cost per item? Or is it going to be even more expensive? And you can see that diseconomies of scale are relatively rare. In this data for wastewater treatment, there's only a handful of things where the value is greater than 1. The laboratory happens to be one of them. And you can see that the laboratory for a big wastewater treatment plant costs more than the laboratory costs associated with a smaller wastewater treatment plant. And that could be related to the bigger the treatment plant, then the federal government has like stricter regulations for how closely they monitor their discharge. So it could be related to that. So let's try it out with this illustration where we're going to get a taste of using these correlating exponents. We have a 0.5 MGD wastewater treatment plant. Now that's the indication of the capacity. and we know the cost for that capacity. And so that means that C1 is 1.9 million, and Q1 is 0.5 MGD. All right, so let's put that on the whiteboard here. Breaking down the problem statement. C1 is 1.7 million. Q1 is 0.5 million gallons per day. That's what MGD stands for. So that means that wastewater treatment plant has 500,000 gallons per day coming into the treatment plant, and when it was constructed, it cost $1.7 million. The correlating exponent, X, is 0.14. So if we want to find the cost of the 2 million gallon treatment plant, that means C2 is our unknown, and the capacity that we want to know is how much is it going to be for a 2.0 MGD plant. All right, so C2 will be C1, which was the 1.7 million, and the ratio of the capacities is 2.0 MGD divided by 0.5 MGD, and then we're taking it to the power of 0.14. Okay, so can I get you to check that? I have it here on the projector that it should be 2.06 million, but let's just see if it works out that way. Okay, so it's going to be 4 to the power of 0.14, and then I multiply that by 1.7, yeah, 2.06 million. So it's not that much more expensive because that correlating exponent is so far below 1. I mean, think about it. We're building this treatment plant, it's going to be 4 times as big. Instead of treating 500,000 gallons per day, it's treating 2 million gallons per day. So that's a 4 times increase in size. But did the cost increase by 4 times? No. It's a nonlinear relationship between the increased size of the treatment plant and the increased cost that's required to build it. So you can spend 1.7 million to treat 500,000 gallons per day, or for just a little bit more, for 2.06 million, you can quadruple the capacity of the treatment plant. And sometimes that's, you know, when you're standing in line at McDonald's and they ask you, do you want to supersize it? And you think, oh, okay, I can get double the size of the drink, 5 times as much fries, yeah, and it's only 70 cents more, I'll go ahead and supersize it, of course. You're supposed to always say yes when they ask you that. I saw a movie that the guy went to McDonald's every day for a month, and anytime they asked him, hey, do you want to get a, supersize it? I'm sure you maybe heard of the movie. He did it. It wrecked his health. So any questions about cost capacity equations? All right, so here's the table in your book that has all the detailed information for different components. In the handout that I've given you, Part 2, we're going to combine cost index and combining cost index and the cost capacity ideas together. So let me bring up the problem statement here on the screen. Maybe I've got it here. So we're going to look at 3 components that go into the cost of a wastewater treatment plant. We're saying we have some data from back in 2010. And so in 2010 we had the aerated lagoon, and we know the size of the aerated lagoon, and we see how much it was back then. We know the blower, the capacity of that blower, and the cost of it back then, the pump, the capacity of the pump, the cost in that year. And so here, what we're going to have to do is find out the cost of each component and how it's changed over time. So find for the aerated lagoon, what's the 2017 cost? And you can see the formula here is you're going to use the data, C1, the cost from 2010, and then you take into account the difference in size using the ratio of the Q's and the correlating exponent. And then you also correct for the changes in pricing over time. So we know the cost index in 2017 was 164. The cost index in 2010 was 137. And so you're going to take this cost of what something was when it was a different size and a different year, and we're going to make two corrections for each of these components. We're going to make two corrections for the lagoon, two corrections for the blower, two corrections for the pump, correct? And when I say two corrections, I mean the time correction and the size correction. And then we're going to figure out what is the cost of each component in 2017. And by the way, on the handout, if you turn the page, it has the correlating exponents that you need. So the correlating exponents are on that third page. It's a virtual certainty that a question like this will appear on the final exam. All right, so the aerated lagoon is going to cost $12 million approximately. And the correlating exponent, this 1.13, of course, you have to go to the table and find, what is described by the item in question. And so we're talking about an aerated lagoon, so we go here to the table and find, let's see, where was that? Lagoon aerated, 1.13. And you can see that I kind of, as an intermediate step, I found what's the effect, these two factors. And so the size difference means that you're going to have 3.13 times as much cost. So that this first number that's in parentheses is related to the size difference between this large one that we're trying to price out and the small one we have the data for. And then the second factor is related to how prices have changed over time. And so that's the cost index associated with us working in 2007 instead of 2010. The cost of the blower is going to be $733,968. And the cost of the pump, $291,104. So overall, we would estimate that to construct this in 2017 for the different sizes that have been described, it's going to be overall $13,490,000. Everybody else get the same amount? Yeah? All right, good. Let's talk about one other way of estimating costs, another tool in our toolbox. It's called the factor method. And so the idea here is that you can predict the entire cost of the project by looking at just the cost of one component and then scaling it up from there. So here's the formula for it, but I'll tell you how I noticed this was the case. I used to live over in Dubai, and I'm sure most of you seen pictures of like all the fancy buildings over in Dubai, and like they have awesome beaches. It's a great place. One of the things about Dubai is it has some pretty expensive restaurants, and sometimes you'd go into a restaurant and you wouldn't really know in advance it was going to be expensive. But what you could do is you could just look at the cost of how much a bottle of water costs, and your meal, I found over time, your overall meal is about to be probably 10 times the cost of a bottle of water. So if I went into a restaurant and they're charging $2 for a bottle of water, then that means ballpark I'm probably going to spend $20 on the meal. But sometimes I'd go into a restaurant and I'd see on their menu they're charging $10 for a bottle of water. And so that tells me, well, this is going to be a $100 meal. Maybe I'll go find someplace else to eat. So the idea there is that you can predict an entire thing, like the cost of a meal, which has many more components than just water. You know, it's not that I was going to order 10 bottles of water and that's what my whole meal was. It was just that the cost of one thing is broadly representative of the expenses that you're going to have for other components as well. So what this is saying is you find the cost of some component, some major equipment, and you find a cost factor H, and so if routinely you're spending a certain percentage of your overall budget on one component, then you can use that relationship to predict things in the future. So if I was spending 3 dirhams on a bottle of water, then probably the meal was going to be 30, but 20 dirhams for a bottle of water, then the meal would be 200. So that's kind of the illustration of the factor method. Now, here is the full-fledged factor method that takes not only what I just described into account, the cost of the major equipment, but then it's also correcting for the indirect costs. We talked about indirect costs in class on Tuesday. Does anybody remember what sorts of things are considered indirect costs? What is it? Rent. Okay, good. And remember that the definition of indirect costs are those costs that aren't directly related to a specific level of activity. So, you know, like the production of Twinkies example, direct costs would be the flour that goes into the Twinkies, because you know exactly how much flour, how much sugar, how much packaging. Those direct costs are specifically tied to what's being produced. But the indirect costs are where it gets a little bit fuzzy on how much you need to make a certain amount. So we don't know, in the case of rent, you don't know how much rent it takes to produce a box of Twinkies. Probably some, but you don't know exactly on some of those costs how to directly allocate it. So instead we just use percentages. And here what that's saying is you can find the total cost for an entire project by looking at the cost of some major equipment item, and then these direct cost factors that we're talking about is we're saying, you know that if you're spending a certain amount of money on a concrete pad, and all of the other expenses for the project can be somehow tied as a percentage of that one item that you do know the cost of, then you'd add up those direct cost factors and you'd multiply it by the C sub E, and then on top of it, you're taking the indirect cost factors into account. So I think this equation will probably make the most sense if we look at the third part of the in-class exercise. All right, part 3, factor method. So we're saying that a new diesel generator will have a cost of $975,000, and the cost factor for the concrete pad is known. The cost factor for operating training is known. So if we grab this formula, let me grab the formula and paste it in here. All right. The C sub E is the cost that we know. That's $975,000. And then F sub DC is there are factors with other direct cost items. And so the other direct cost items that we know for this project besides the diesel generator is the concrete pad and the operating training. So You add those other factors along with 1, and 1 represents the diesel generator in this case. It's the item that you know the cost estimate for. And then what we're told is that the indirect cost factor is 0.27. And so that's going to be here F sub I. So let's find the total cost of putting the generator into service. So there's going to be 3 costs in this project. There's going to be the diesel generator, the concrete pad, and operator training. And so $975,000 is the diesel generator. And these other percentages, what it means is we're saying that generally, however much we spend on the diesel generator, for every dollar we spend on the generator, we spend 16 cents on operating training. And for every dollar we spend on the generator, we spend 39 cents on the concrete pad. So you can see that those direct cost factors are added together, and then we're multiplying it by the cost of the thing that we know. And so the thing that we know is the diesel generator, $975,000. And then over and above that, once you find all of the direct costs, what we're saying is that we have to add an additional 27% to cover the indirect costs. And so that would be the expense of human resources, the expense of maybe insurance, the expense of the accountants who are ordering all of these things and coordinating the delivery. So in the end, the total cost is going to be $1.91 million. So that is the factor method. Any questions? All right, that's all I have for you today. Let's take one last look at these announcements. The assignment that you have for cost estimation, that's due on Thursday, the 29th of November. I'd suggest just maybe finish it up even before Thanksgiving. You know, while it's still fresh in your mind, it'd be a lot easier to do now rather than after you get back from Thanksgiving. If you've got any questions as you're working on it, please feel free to stop by my office. I'd be glad to help you. Otherwise, I'll see you like 9 days. You know, I'll see you after Thanksgiving. Hope you have a nice break.